Hey everyone, this is going to be a follow-up to the relaxation time for chemical reactions video that I did previously, and also a highlight of where this material is coming from. I am getting this material from the textbook you see right here. I'm just going through it and looking at some of the examples that they have and going through those. Now, what you see me doing in these videos is not going to be exactly to what's in this book, because frankly, sometimes what the book gets to, it itself within the book doesn't explain thoroughly enough. It's one of those, go on from here and kind of prove it yourself. So I usually reference things online for that, and I will show the sources for that when I get to that. For the time being, we'll go back to relaxation time and talk a bit, because I have a more concrete example of where that time constant, that tau, comes from. So you'll remember we defined this relaxation time term right here, and how that's where either you have a system that's decaying, and when it gets to 1 over E, or about 36.8% of the decay, that's what this tau is, regardless of any of the other factors. Or if you have it where something's being generated, like in the case where you have a reaction here where A can become B, or B can become A. It's going both ways, it's reversible. This is an example of A dwindling as it becomes B, and this is an example of B growing because it's being formed by A. And you see that tau constant would be the same between them. This is going to be 1 minus 1 over E when something's being formed. So we'll move on. So the scenario we're looking at is where you have some reactant named A, and whenever you have something in equilibrium, you're never going to get a full conversion from A to B in most of these reactions. It's going to be where B can then go back to being A, and they'll meet some equilibrium over a sufficiently long time. And that's why we have these constants here for. So K is the rate, it is a rate constant for A turning into B, and this K prime is for when B becomes A. And so we can form a differential equation for the formation of A with respect to time, or how its concentration changes. And this is simply the rate of A, this is actually the rate of B forming, because you see here K is going from A to B. So when you have the negative of that, that means that B is being formed. So you're losing A in this case, which is why you have that minus sign. But over here, the K prime of B going in the other direction, this means that B is going back to A. So this is basically A leaving or A being formed. And of course, you're looking at that as it changes with time. And if we say, so we're going to say that this A of T, is a function of time. So at time 0, it's just your A naught, whatever your initial concentration was. And so we know that because of conservation of mass, at any time when you're looking at the system and you see how whatever this A naught is, like when you're at 0, this B goes away. It's just going to be A equals A naught, and then B will form, but nothing else is coming into the system. So this is going to be equal. So you can say that B at any point in time is equal to whatever all of that initial starting reactant was, minus however much you have now, because whatever you have, if you're missing some of this because your A is smaller, it's because it became B. And so now we have this equation down here. You just substitute this in, Ka, and then this is directly where the B went. And then when you distribute this, you get this term here. And that brings us to this differential equation right there. So when we had it in this form, so it's dA over dt equals this. You can bring the A's over to this side. You bring this whole thing down here by dividing both sides by this. And then you multiply both sides by dt. And so we're going to do an integral. This is just going from 0 to t. Start at time 0, end at whatever time you want. So this will be nice. It gets rid of the constant c for us. And here we're starting at whatever our initial concentration of A was, and we're ending at whatever concentration of A you would get after a certain period of time. And so to solve this equation, you can do a simple U substitution, because if you're differentiating with respect to A, which we will be, it just becomes this. And then you say what your dA is. So you replace the dA by this term right here. This is a constant, which is why it can be brought up front. There's a U down there. And then this didn't change. And obviously you would put these limits of integration here if you wanted to, but I didn't bother doing that. It's laborious, and you can get to that at the very end. And you get something in this form right here, which does look pretty messy. Like the integral of this is a natural log. And after that point, it's mostly just a matter of plugging things in. If you guys want a derivation for this, I can show you, but it is kind of of like algebra autopilot. The important part comes at the very end here where we define this AEQ. That's the equilibrium of A. So when you have this final form down here, you know, you do a bunch of stuff and then eventually you get down here where it's all done with. Take the limit as time goes to infinity. That's going to be your equilibrium value of A. And you'll see the t is up here. When that goes to infinity and the minus sign, this is basically going to become 1. And so you have this right here, how whatever your equilibrium value is, it's equal to, I don't know why that's there. It's equal to your concentration of A initially with these constants. And while we're speaking about these constants, the constant of A going to B, or the constant prime here of B going to A, we're going to define this equilibrium constant K as the ratio between B in equilibrium and A in equilibrium, which is K over K prime. That's your equilibrium constant for the system. The reason that's important is when we move on to the next stage here. And so we'll make a note of this. In this case, we're going to be looking at a system, and I'll put in the illustration for this, a system where you have a sudden change in temperature or pressure which makes the system behave differently. So we have this this form here. So first off, at equilibrium, when we have something at equilibrium, it means that, you know, like this isn't changing, you know, change of the concentration with respect to time. Well, it's not, because it's being formed by B going back to A at the same rate at which A is being turned into B. And so this would be equal to 0, and these terms would be equal. And that would be the same when it's at one temperature and at another. This is what this T2 means. You'll see it on the graph later. But our equations, when you have a certain temperature, are shown here. The instant that changes, you have it still being the same. But then the relaxation involves this x value that we need to solve for, and then you get to the second equilibrium over here. So that's where we get these equations. So now the change in A with respect to time is going to be equal to the constant at A2 times our relaxation. The same thing for B over here. And the minus again is because A is being formed into B here, B's going back to A, and that's how they meet up with each other. And because we have this definition up here from the equilibrium constant, which I think that should actually be EQ2, yes, B going down to A, you can just multiply these out. So you see these are equivalent up here. We get a substitution in here. This gets substituted to that, which you can then get rid of. And so all you have is this form right here. And so now we're kind of doing what we did before, where the concentration of A is going to be equal to whatever the concentration would be of A in that second equilibrium plus that relaxation factor. If you derive both sides with respect to A, you get dx, because this is a constant. So then if dA is equal to dx, well, dx over dt is equal to dA over dt, which we mentioned earlier is going to be this form right here. So dx over dt equals this. You're going to do the same thing as before, where we divide both sides by x and multiply both sides by dt to get this equation right here, which you can then integrate. And same as before, whatever this x term is, you're going to start at x of 0, the initial x, and go all the way to whatever x value corresponds to the time, which starts at 0 and just ends whenever you want it to end. And then again, natural log, this is what it evaluates to. Doing the exponent on both sides gives you an equation of this form. And then you'll see here that we have these constant terms here, and we just call them this tau. This is our relaxation time, and this is where they come from. So when you have something that's being disturbed from equilibrium and you're trying to look at the amount of time it takes, and you'll see the graph looks very similar to the graphs that we had before of these. It looks like this one, where it goes up to a certain time, then reaches a different equilibrium. When you want to see how long it takes, you'll find this tau here, and this is where it came from. So thanks for watching.